In this video, I'm going to talk about how to divide using divide instruction. There are three formats we can use if we want to put a dividend inside AX, or when we divide, we're going to have quotient, we're going to have a remainder. If we use AX, the result, the quotient part will be inside AL, the remainder will be inside AH. If we want to use the second format for divide, we can put a dividend inside DX and AX, then divide by the same size divisor. After this, the result will be quotient inside AX. The remainder for the division will be inside DX. We also can use EDX and EAX for divide to hold the dividend in EDX and EAX. I use the same size divisor, can be register, can be a variable. The result quotient part will be inside EAX and the remainder will be inside EDX. We have an example here. Divide 8003 by 100 using 16-bit operands. So let's see the format. 16-bit, that means we're using the second format. DX help out with AX. Okay. So we first set up DX with 0 because DX is the upper half. AX is going to be the lower half. 8003 can hold totally in AX, so we set the DX to be 0 to clean it up. Because later DX is going to hold the remainder for division, so you have to make sure DX start with a clean 0, even if you don't have anything put in DX in the beginning. The CX is going to be the divisor. So the divisor is 100H. If you use 803H divided by 100H, you're going to have quotient 8 and the remainder 3. Quotient 80 and the remainder 3. So this is the divide instruction. So the setup is very important, after you set up right, you can say divided by CX. AX holding the quotient 0080H, the remainder is DX3. To do the same divide, we can use 32-bit operands. If we use 32-bit operands, and this is what we're going to use, so we're going to clean up EDX. The remainder will be inside EDX, and the quotient will be inside EAX. Okay, so clean up EDX from very beginning, and move 803H into the dividend EAX. Then set up ECX as a divisor, then div ECX. The quotient is still 80. This is 32 bits, 8 has a decimal digits, so we put 60 before 8. And the remainder is 3. 3H or 3B are the same, so you don't have to put H or B there. You can try this one on yourself. Use 16 bits. Your divisor is BX 100H, and your number is 0087 with 6000. So your dividend has two parts. The upper half is in DX, the lower half is in AX. So this number is bigger. You have to put some in AX, after that put into EDX. So it's like this is a number 0087 6000. So when you divide by 180, that means you're going to take away 2 zeros from the end. And your result will be 8760H UDS is nothing, because the result 8760 hold totally inside AX. Then DS is 0. Another divide. This one is a divide overflow. The reason, let's see. So you put 080,006,002 divided by 10. Your result cannot feed into the destination. Okay. That's why. For standard integer division, we use I-divide. The three formats still can be used, but it's a little bit different. To divide, we have to use CBW, CWD, CDQ instruction. They are going to do the sign extension. If we use, for example, let's take a look. If we use AX for dividend, we have to do a sign extension from AL to AH. Same thing, if we use DX with AX, we have to make sure DX get a sign extension of AX before the divide. Do sign extension for UDS before the division, and you need to get sign extended into UDS before you use UX for dividend. Okay, here we have an example. Variable D word variable is assigned double word -101. This is a hexadecimal format. In the code, we're going to copy double word value into register UAX. Then we do CDQ. CDQ means convert a double word to quad word, because ES is just a word. We need it's a double word. We need a quad word. We're going to use EDX. So we do sign extension, put whatever is the sign in EX into EDX. The sign of EX is negative, that means it's 1. So if we extend all the ones into EDX, that's going to be FFFF in the hexadecimal format. Here, we're going to divide -48 by 5. -8 divided by 5. Okay. The quotient and -48 divided by 5, you put the quotient 9 is 45. Then you have remainder -3. So -48 divided by 5, the quotient part is -9, the remainder part is -3. AH is holding the remainder because we're using AB's dividend AL and use AB's divisor BL. So we want before we use I divide, we have to do sign extension, and we use CBW. CBW means extends the sign from AL into AH, and that also means convert by to double to word. You also can use a 16-bit division if you dividing -48 by 5. So if you use 16 bits, you have to use CWD. CWD is going to convert the word into double word because AS plus DS is 32 bits, so there are double word. So we have to do sign extension CWD. Then we move divisor 5 into BX, then use I divide BX. That means AX divided by BX. The same result like last one. To do the same task, we can use 32-bit division. That means you're going to use EAX with EDX. Of course, you have to use CDQ. Size turned from double word in quad word. That means size turned from UX into EDX. Your divisor use EBX, then divided by 5, and this is the same result. You can try this one on yourself. You're going to divide a negative 513 by 100H. 100H, let's see how much, let me calculate. 1 is 16 to 1 times 16 to the second power, that's 256. So here this is what? Let me put a note here. This is 256. 100H is 256. So negative 513 divided by 256, the quotient part you're going to have 2, because 2 times 256 is 512, and your remainder will be negative 1. So negative 513 divided by 256, your quotient is in AX is negative 2, that's right. Your remainder is negative 1, that's right. So this is a huge number. If you do it in hexadecimal, it's not easy to figure out. But if you do it in decimal way, it's easy to tell the answer is right. We can convert arithmetic expressions into assembly programming language, and we try to add and subtract in previous chapters. In this chapter, after we have learned how to multiply, divide, we can incorporate multiply and divide into arithmetic expressions. Here, let's take a look at this example. In this example, we're going to add up variable 1 with variable 2, then multiply variable 3, then assign the result into variable 4. To do this, let's see the coding, and copy variable 1 into EAX, then add EAX with variable 2. That means EAX is holding this addition's result. Then multiply variable 3. That means EAX is the dividend now, and is the multiplicand, and variable 3 is the multiplier. So this is a multiplicand in EAX, and this is a multiplier. And after we multiply together, the result is going to be in EAX. Jump carry, if it's too big, check for carry. That means if carry flag is 1, and you're going to jump to a label location called too big to process. Otherwise, if everything is fine, you continue here, copy EAX into variable 4. That completed their task. Let's see 2 more examples here. The first one is going to have negative variable 1 times variable 2, then put together, add into variable 3, then set into EAX. To implement, we can copy variable 1 into EAX, then neg EAX, that means change variable 1 into negative. Then use IMUL variable 2, because this is a signed number, so you have to use IMUL. Jump overflow. Overflow is for signed number, so that means if it's too big, the result too big to hold inside EAX, you're going to jump to location too big to process. Otherwise, when you stay here, you're going to add EAX with variable 3. And finally, you're going to, you don't have to assign, it's automatically inside EAX. When you add EAX with variable 3, and maybe your results also too big, so you can say, if that's the case, jump to a location too big to process. Another example, we're going to time variable 1 with 5, then divided by variable 2 minus 3. So there are two paths. We go by the priority rules. So you do parentheses first and do the second parenthesis. Then you divide the two parentheses results to set into variable 4. So let's see the coding. And variable 1 get into EAX, that's fine. Then move EBX with 5, so that means you put 5 into EB. Use IMUL EBX. So they are treating variable 1 as a signed number. They use IMUL, that's fine, no problem. The second part, they're going to do the second part inside EBX. Copy variable 2 inside EBX. Then use EBX minus 3. So EBX is holding the second parenthesis result. EAX is holding the first one. So we're going to use IDIV. So EAX is the dividend and the EBX is the divisor. Finally, we put the divided result EAX inside variable 4. I think there's some mistake here in this PowerPoint. Since this is I multiply, the result also is going to overflow into EDX. So you have to, I guess somewhere you have to make sure your EDX is 0 before you multiply. If I am doing this coding, if I want this to be 100% right, I will set up EDX with 0 from the very beginning. Otherwise, the result could be wrong. We tried this in class. Yeah, if you're missing something like this, when you do programming, you will see the result is totally off. So pay attention for the EDX, because EDX is helping EAX to hold the multiplication or division result. So before you multiply, when you do it this in this area, you need the EDX to be there. However, when you do divide, you need to do substitution to EDX. So here there's another missing another key statements. You're supposed to say CDQ EDX. That means put the sign of EAX into EDX. Otherwise, this code won't work. So this line I would say is important. Okay, don't miss this line. It's going to be in trouble. I think this line is also missing in the book's PowerPoint. And we have tried in the regular class. This should be there. Okay, to make the code run. Otherwise, you may have trouble work around. Thank you for watching.